Ladies and gentlemen, good morning. We are team CN335 from the Department of Computer Science and Technology of Tsinghua University. My name is Hu Zecong, and my teammates Wei Yilong and Yang Tianlong. Okay, so, oh, sorry. Oops. Oh, okay. Yes, the three of us. And our contest project is Fpga-based 3D AR CAD system. So the motivation behind our project is to simplify 3D modeling. And well, we may be familiar with building sand castles or using Lego bricks. But when it comes to drawing shapes on computer, things are completely different. So what if we combine computer-aided design with how we could create a model in reality? Well, can we enable our users to create 3D models just as if they were building a model in reality? Well, of course, because we have HoloLens from Microsoft and many other products. But they're all too expensive for an ordinary consumer. So here's our idea. Can we build something similar, but maybe not so perfect, but much more affordable? And so we present our work, the Fpga-based 3D AR CAD system. Maybe it looks a little bit less impressive, but it does almost the same thing. Well, we can draw with a pen in the air and create 3D models, just as in reality. So our system is consisted of one Terasic development or DE2I150. And we have two external cameras and one screen. Well, it works by recognizing a drawing pen using the two cameras and then locating its real-world 3D position. The user could interact with our system using a remote control. So now let's start our demonstration. Due to limitations of this stage, we can only show you a video. Okay, so this is a video of us operating our system. And well, he just uses this remote control, as we can see in the monitor. And you can see that the spheres drawn have this occlusion relationship. Well, if you draw this sphere nearer to the monitor, then the sphere will appear in the front, and otherwise at the back. And the remote control can also be used to change colors, and we can also draw cuboids instead of spheres. Okay. Okay. So let's talk about the algorithms of our system. So first, let's talk about our recognition algorithm. Well, that is, how could the system recognize what the position of the pen is? Well, note that by pen, we actually mean this lollipop shaped thing, as you might have noticed in the video. Oh, I'm sorry about that. Okay, this thing. Well, it is a 3D printed thing, and I'm sadly to say that we constructed it using traditional 3D modeling techniques. And we painted the circle part with special color, which is using recognition. Well, instead of searching for the shape, our recognition algorithm actually searches for patches of this special color, and then uses the largest patch as our detection result. And I'm going to illustrate the workflow of our recognition algorithm, if this would please turn to the next page. Okay. So this is our camera source image. To be specific, we first turn this source image into HSV color format and then binarize it. Okay, binarize it, please. Okay, binarize it. And the binarize and HSV conversion is implemented using hardware logic only, because this could accelerate the performance greatly. And after that, the rest of the algorithm is implemented using the NEOS system. And after binarize, we should denoise the image using erode and dilate operators. And finally, the blood bill algorithm is applied to find the largest patch. Okay, so now we know the coordinates of the pen on both cameras. So but they're actually coordinates on the screen, but not in the real world. So we have to find the real world coordinates. And this is done using a simple formula from stereo vision. Oops. Okay. This is just a little bit of geometry. And here we need the intrinsic parameters of the cameras, and which is done by an offline camera calibration algorithm, which is implemented using OpenCV. Okay, so next let's talk about the rendering algorithm. Well, we implemented the whole rendering algorithm using the NEOS2 CPU, which is not a good idea because the NEOS2 performs fully when you use it to do floating point arithmetics. But we had no choice. We tried our best to put hacks and tricks into our algorithm, but the result is not very good, and we still take about a few seconds to render a single object. And so let's get back to the algorithm. Well, the first step of rendering is to project the rendered object onto the screen, which is, as the formula here illustrates, it is just the reverse of the positioning formula which we've seen just a moment ago. And the next would be to handle the object occlusion. We use the Z buffer here, and we store the closest object and its distance from each pixel to the point of view, and this is called a Z buffer. Each pixel in the rendered object is then compared with the corresponding objects in the Z buffer to decide which comes first, which is in the front. And also, the whole rendering process is parallelized to run on 3 separate NEOS cores. Each core renders a separate part of the object, so it could speed up the rendering process by about 3 times. Okay, I'll leave the stage to my teammate Wei Yidong to talk about the hardware part of our design.
Okay, I'll talk about our hardware. This is our overall architecture. We divide the system into 3 parts. The first part is the data input. The input of the camera, we configure it to output an VGA resolution image. We encoded it into Avalon ST, and this is then converted into HSV. The HSV format enables us to find the specific color in a single comparison. Then the HSV is then binarized and then stored into the memory. Also, the original image, the RGB one, is also stored into the memory. Okay, now comes the data storage. We utilize SDRAM and SSRAM on the development board. The SDRAM is used to store the camera image, the rendered image, and the buffer. SSRAM is used to store the GUI overlay. Also, to avoid image flickering and tearing, triple buffer is used to both camera image and GUI overlay. Also, dual clock FIFO buffer is used as a cache, and it enables performance burst because we use the capability of the SDRAM far more better. Now the data output. The composer receives 3 Avalon STs, that is the camera image, the rendered image, and GUI overlay, and finally outputs to VGA interface. Thank you.
Okay, so we're running out of time, so I'll skip this part. It is written in the paper, so you can have a check if you want. Okay, so I will say a few words before this ends. We spent over 4 months on this project, and we started with only basic knowledge in digital logic design, and up until now we can design a fully featured digital logic system. So I think we learned a lot, and we would like to thank Altera and Terrasec for giving us such wonderful opportunities and also providing such excellent hardware. And also I would like to thank you all for your attention. Thank you very much.